CH-54 pilot transition class at Fort Rucker, Alabama, includes aviators with thousands of hours of rotary wing flying experience. Yet, despite their background, it will take these men 6 weeks of intensive training to become qualified flying crane pilots. One good reason for this is that the CH-54 is a unique aircraft with many features not found in other helicopters. In addition, the scope of the missions and the world areas in which CH-54s are now operating increases every day. In this film, designed for future CH-54 pilots and crewmen, we will present and compare some of the basic characteristics of both the CH-54A and the newer CH-54B. The CH-54A with the rotors at the extreme positions is 88 feet 5 inches long. That's almost 30 yards. The weight of this aircraft with load levelers and hoist installed is about 21,000 pounds. However, the gross takeoff weight of the CH-54A when carrying a full load, including the crew, fuel, and a pod filled with cargo, can be as much as 21 tons, 42,000 pounds. The tail rotor system has 4 blades, a tail rotor gearbox, a tail rotor hub, and a pitch change mechanism. The main rotor has 6 blades, and the main rotor disc diameter is 72 feet. When the blades are stopped or turning at low speed, droop and anti-flapping restrainers limit the downward and upward movement. A unique feature is that each main rotor blade spar is filled with nitrogen pressurized to about 10 pounds per square inch. A color-coded pressure indicator at the root end of the blade shows if a spar crack or seal leak has allowed the pressure to drop below acceptable limits. This blade inspection method is called BIM, and the indicator can be checked out using a test lever. 2 other features common to all Tarhees are a full swiveling nose wheel with self-centering device and an electrically retractable tail skid. This makes it easier to move a load under the airframe for 4-point hookup. In addition, the CH-54A can kneel and jack its main landing gear through 8 inches of travel to assist in pod and 4-point hookups. This helicopter is powered by 2 gas turbine engines mounted side by side on top of the fuselage. 2 engine air particle separators can be installed in front of the intakes to protect the engines from sand or other foreign matter in the air. Each engine has a separate but interconnected fuel system for cross-feed capability. The fuel controls automatically feed the turbines with the precise amount of fuel to develop the power needed to maintain a constant rotor RPM under varying load conditions. Each engine in the CH-54A is rated at 4,500 shaft horsepower. The pilot's compartment can seat a crew of 5. A normal complement, however, is 4. The pilot and co-pilot face forward. The crew chief and a 3rd pilot are in the aft section. The aft-facing pilot can fly the aircraft when the CH-54 is using the single-point hoist to pick up or lower a load. The aft-facing pilot normally controls the hoist. He has a clear view of the pickup point and can lower the hook precisely over his target. Now here's the pilot's view of the instrument panel and controls. The key instruments are right in front of you. Note that at the bottom center, under the torque meter, there is a unique triple tachometer. The three needles read in percentages of total RPM. Needle number 1 indicates the percentage of N2 on the number 1 engine. Needle number 2 does the same for the number 2 engine, and needle R indicates the percentage of the main rotor RPM, the NR. Note also the position of the hover indicator at the bottom left. Later we will use it to check out the automatic flight control system channels. Located on the center console are the communication and navigation radios, the master switches, cargo hook and hoist controls. Also at the top center, we find the fuel management panel. The cross-feed fuel system allows you to feed fuel from either or both main tanks to number 1 or number 2 engine. Note that there is no cross-feed between the main tanks. However, there is an auxiliary tank, and its pumps will transfer fuel to both main tanks. Two fuel shutoff levers, one for each engine, are on the overhead control panel. Pulling a lever to the full aft position shuts off the fuel supply to the respective engine. The CH-54 can be pressure defueled and may be pressure refueled to the level set by the limit bugs on the fuel quantity gauges. The fuel connector is located on the bottom of the left landing gear support. Going back into the cockpit, here is another important part of the instrument area, the caution advisory panel. It can flash 51 different messages concerning malfunctions and operating conditions. Operation of the lights can be checked by using the panel test switch. Let's look at some more key systems. Here, directly behind the main gearbox on top of the aircraft, you can see the auxiliary power plant, which is actually a small turbine. The function of the APP is to drive the accessory section of the main gearbox when the main rotor is not turning. This permits starting of the engines and provides hydraulic and electrical power for ground operational checks of the single-point hoist controls and other systems. The same accessory gearbox also drives the two generators that are part of the electrical system shown here on a training aid. Other components of the electrical system are two transformer rectifiers and a 24-volt, 22-ampere-hour nickel-cadmium battery. The battery compartment is in the nose section and is readily accessible. The battery recharges when the APP is operating or when the main rotor is turning. In addition, there are external receptacles available for both DC and AC power inputs from external power sources. Here on the center console are the electrical system master switches. Note that the battery is turned off when DC external power is plugged in for a long time. This keeps the battery from being overcharged. However, when there is no DC external input, always leave the battery on. Otherwise, the generators cannot recharge the battery. The APP controls are located on the overhead control panel. Here's another point. After starting the APP, the accumulator that drives the APP starter motor is depleted and must be recharged. This may be accomplished in one of two ways. One, by using an engine starter to motor one of the engines. Or two, by actuating the single-point hoist system, whose hydraulics are also linked to the APP accumulator. However, if the APP fails to start, its accumulator must be recharged manually. This is done by using a small hydraulic hand pump that is part of the system. On this subject of hydraulics, we remind you that all the hydraulic systems of the CH-54 are described in your operator's manual. You should remember that the utility hydraulic system is an extremely important one. It supplies hydraulic power to the wheel brakes, the load leveler release system, the first stage of the tail rotor servo, and the automatic flight control system servo. Considering all of its various systems and components, the CH-54 Tarhe is one of the most sophisticated aircraft operated by our military services. It requires more than 300 pre-flight checks and actions to be taken before takeoff. As an example, let's look at some of the checks made to test the fire warning systems. On all except earlier CH-54s, there are 2 fire detecting systems for each engine and 1 system for the APP. The warning lights are tested before every engine start. Master fire warning lights are located on the instrument panel, 1 in front of each pilot. A fire warning light for each engine is located next to the respective N1 lever. Also, the APP has a fire warning light. Now, assuming the many pre-start checks and preparations are completed, you are now ready to start an engine. Begin by holding the N1 in the shut-off position and engage the starter. If fuel vapors are present, they will be discharged through the engine as N1 RPM increases. After N1 RPM increases to 5%, turn ignition on. When the N1 tachometer indicates 12%, move the N1 lever to ground idle. Fuel flow begins at this point. The T5 should indicate a light off within 20 seconds. But if it doesn't, you must immediately pull straight out on the N1 lever, return it to the shut-off position, and follow the prescribed abort procedure. Make a point of anticipating a failure to light off and react immediately and correctly should the condition occur. Otherwise, you may have a hot start. Here's a typical takeoff to a hover. Note that it's made vertically to a sufficient height to keep the wheels clear of the ground. When the wheels have about 10 feet clearance, use the cyclic to prevent drifting away from the hover spot. To start your flight from a hover of about 10 feet, here's the procedure. Apply forward cyclic and use the collective to maintain altitude until your airspeed is enough to get translational lift. Normally, this will occur at an airspeed of around 20 knots. Now continue to apply forward cyclic to accelerate the CH-54 smoothly to 70 knots or whatever airspeed the load and conditions will permit. Then adjust power for the desired rate of climb. Use the tail rotor to hold the direction of flight and the cyclic to control drifting. Above 50 feet, allow it to crab into the wind. This has been a typical takeoff. Variations may be necessary depending upon load configuration, terrain factors, density altitude, and other variables. Now let's take a look at some special features of the CH-54 flight control system. An automatic feature that reduces the amount of pedal needed to compensate for changes in collective pitch is called the collective to yaw coupling. This coupling automatically causes tail rotor blade angles to increase when the collective is raised and to decrease when the collective is lowered. Another feature that is a big help to Tarhe pilots is the automatic flight control system. It keeps the aircraft level, on course, and at a constant altitude. Although the AFCS is normally kept on at all times during flight, the pilot can override it whenever he wants to. The control panel for the AFCS is on the center console, between the forward-facing pilots. There is a yaw control knob to make fine adjustments in the flight direction and a CG trim knob to reset pitch channel authority for varying flight conditions. To keep the altitude constant, the barometric altimeter button is depressed. This engages the altitude controller. Release switches on the cyclic grips will instantly disengage the AFCS should you experience channel malfunctions in flight. The off and on switches for the AFCS pitch, roll, altitude, and yaw channels are on the overhead control panel. These switches are normally kept on, but may be selectively turned off should individual channels malfunction. During flight, channel operations of the AFCS can be monitored by observing the hover indicator. It has a vertical bar, a horizontal bar, and 2 pointers. Yaw and altitude are shown on the pointers, pitch on the horizontal bar, and roll on the vertical bar. Here the horizontal bar shows that the pitch channel needs adjustment. The CG knob on the AFCS control panel is used to bring the bar back to center. This adjusts the AFCS pitch channel authority to compensate for changes in the flight condition of the aircraft. As shown earlier, hydraulics and servo systems provide the force needed to operate the main flight controls and the AFCS servo. As a safety precaution, there are 2 separate hydraulic systems used to control the main rotor servos and 2 separate systems used to control the tail rotor servo. Switches on the pilot's and co-pilot's collectives let you shut off either system if it is malfunctioning. However, an interlock will not allow both systems to be shut off at the same time. The AFCS servo is served only by a single hydraulic system. If it should fail, you will lose the AFCS servo assist. This will be felt as a stiffening of the controls, which will require some extra effort by the pilot to overcome. Should this failure occur, turn off the AFCS and follow the correct emergency procedure. You must learn exactly what to do, not only in the event of hydraulic failures, but in all emergency situations. A separate film covering CH-54 emergencies is available for study. You should be familiar with procedures before making your first flight. Now let's discuss the newer CH-54B and see in what major areas it differs from the CH-54A. First, the engines are rated at 4,800 shaft horsepower, an increase of 300 over the A model engine. In addition, a new main rotor blade provides increased lift. These and other improvements permit the CH-54B to carry a load of 25,000 pounds. The allowable gross weight is increased to 47,000 pounds, 5,000 more than the CH-54A. Some other changes on the CH-54B are dual wheels on the main landing gear. The nose wheel size is the same as the others, so that all wheels are interchangeable. The landing gear no longer has jacking and kneeling capability. In its place, the load levelers have been equipped with separate winches. Using these winches, the load can now be lifted directly off the ground, and the connecting hooks can be brought up flush with each load leveler without having to kneel or jack the landing gear. Internally, improvements have been made to the hydraulic systems, and on the instrument panel, the hover indicator has been modified. The AFCS off and on switches for the pitch, roll, altitude, and yaw channels have been relocated. And additional information will be provided by the Caution Advisory Panel. In the CH-54B, not only will you be visually informed of a major malfunction, but
electrical fault, fire, engine fire, fire, engine fire, serval pressure low, serval pressure low.
These are just a few examples of changes that will be part of the CH-54B. However, the flying characteristics of both models of the Tarhe are essentially the same, and both can be flown from the aft-facing pilot's seat. So now let's see how the controls operate from this position. The transfer of control from the forward pilot to the aft-facing pilot follows a precise communications procedure. You should become familiar with this procedure before attempting to pick up a load in this manner. Note that the AFCS is kept operating on 3 channels, but not on the altitude channel. The aft pilot's control panel shows that he has engaged his hover control stick. Now his cyclic and yaw control movements feed signals through AFCS into the flight control system. His collective, however, is mechanically connected to the forward pilot's controls. The authority of the aft pilot's cyclic control stick is limited. In the CH-54A, pitch and roll authority in all directions from the aft cyclic centered position is 10%. In the CH-54B, this has been increased to 20%. Note that when you move the aft pilot's cyclic away from you, you apply a down motion to the aft end of the aircraft. When you pull the aft cyclic towards you, the aft end lifts and the nose tilts down. A movement of the aft cyclic left or right in relation to yourself rolls the helicopter in the same direction. Another important point. The collective control for the aft-facing pilot in both models of the Tarhe has a direct mechanical connection to the forward pilot's collective controls. Take care not to move it unintentionally during flight operations. Remember, when the aft-facing pilot is flying, either the pilot or co-pilot can override his controls. As a safety precaution, the pilot always keeps his hands lightly on both controls and his feet near the pedals. Finally, here's a quick look at the 3 types of loads flown by all CH-54s. This is the Universal Pod. It can carry a large amount of cargo, 45 fully equipped troops, or 24 litter patients. Note that the pod is suspended by the 4 load levelers and is loosely attached to the aircraft hardpoints. This allows the load leveler accumulators to absorb the vibrations and shocks of flight and landing maneuvers. The pod can be converted to a forward area hospital, complete with operating facilities, and it has also been used as a command post. The load levelers are also used to carry the second type of load, cargo or equipment that can be rigged for 4-point suspension under the airframe. Using a walk-around control assembly, each load leveler can be raised or lowered collectively or individually through 8 inches of travel. This provides for raising, lowering, and leveling 4-point loads. The third load-carrying method, the single-point hoist, is the reason we call the CH-54 the flying crane. The hoist on the CH-54A can raise or lower a load of 15,000 pounds. But with the hoist in a static position, the CH-54A can lift its maximum authorized load 20,000 pounds, 10 tons. On the CH-54B, the hoisting capability has been increased to handle the maximum load for this aircraft, 25,000 pounds. In this film, we have seen some basic characteristics of the CH-54A and the CH-54B. As you continue your training, the many points covered in this film will become even more meaningful than now, and you will soon realize that the flying crane is indeed a unique and distinctly capable heavy lift helicopter.
Attention, attention. Welcome to your new assignment, flying the largest and most powerful helicopters in the free world.
Two key calculations must be made and cross-checked by all Tarhe pilots. One of these is for fuel load allowance. The other is for weight and balance using Form F. Fuel loads carried vary considerably, depending upon several changing factors. As an example, you may have to fly from point A to pick up a 15,000-pound howitzer at B, then fly the howitzer to a mountaintop at C, and still have enough fuel left to continue on to D, the nearest refueling point. The fuel load would be determined by the distance from A to B, the maximum total weight allowed at B, the distance from B to C, the density altitude of the route to C, and finally, the distance from C to D. In addition to varying combined weight of loads and pods, each aircraft will vary in weight depending upon the modifications made and the number of crew members aboard. All these facts must be used by the pilot to calculate his maximum fuel load allowance. The weight and balance Form F determines whether a pod-type load falls within the aircraft's center of gravity limits. Loads must be positioned so that the center of gravity remains within flyable limits for the crane. There are 3 ways of carrying loads with the CH-54. One way is through the use of the universal pod. The second way is attaching a 4-point load to the load levelers. And the third way is flying a load suspended from the single-point hoist system. First, we'll consider pod loads. Pod installation will already have been accomplished. The pilot should, however, carefully inspect installation of the pod before flight. Be sure that the flight engineer has secured the hook to its bracket on the left landing wheel assembly. You should also check to be sure that the crew chief has secured the top part of the hoist cable to clips provided for this purpose on the landing gear and airframe. Be sure that the load levelers are electrically locked. There are 4 load levelers mounted on the CH-54 frame. Two levelers are on each side. And all 4 should be carefully checked. Next, the pilot checks to be sure that installation has left the pod in a level position. There are 4 handling wheels attached to the pod, 2 on each side. All wheels must be retracted and locked in position. If its use is anticipated, the communications cable to the pod must be connected. If you are to carry a Class A load, that is, passengers, you must check to be sure that the screw-actuated safety pins are installed. There are 4 such pins. All 4 are inserted into the pod top from below. And all fit into fork assemblies on the airframe. When all 4 screw-actuated safety pins have been checked, the pilot should be sure that each leveler is manually locked. Again, consult the Form F to confirm that the center of gravity of the pod load is within permissible weight and balance limits. Now that we have some familiarity with the 4-point load leveler system, consideration of loads other than pods is next in this presentation. We are now dealing with attaching a 4-point load to the load levelers. There are 3 ways of positioning the CH-54 so that the load levelers can be connected directly to the cargo. First, the aircraft may be landed directly over a load small enough to fit under the airframe. The second means of positioning the CH-54 is that of taxiing into position over heavy loads that are difficult to move. The practice example seen here is a large tank filled with cement. The third way of positioning the CH-54 over a load is considered to be the best and is recommended when circumstances permit a choice. This is to move the load itself under the aircraft. To provide maximum clearance, start by turning on the APP and using its power to retract the tail skid. The flight engineer takes out the walk-around control and unlocks the load leveler lock-unlock switch. The leveler unlocked warning light will come on. Both the crew chief and the flight engineer must make sure that the truck stays clear of the landing gear. In case of a 2.5-ton vehicle, they line up the rear axle of the truck with the 2 forward load levelers. For other vehicles, the position under the airframe may be different. If the center of the vehicle is moved directly under the single-point hoist, the vehicle is properly positioned. This is done with loads small enough to give plenty of clearance under the single-point hoist hook. If the load were too large, the hook would be secured on the left landing gear assembly. But here there is plenty of room. The crew chief and flight engineer will now pull down and connect the cargo lashing reel cable hooks to the lifting points on the truck. When this has been done to all 4 load levelers, the flight engineer activates the load leveler lock-unlock switch. Locking is verified by observing that the warning light goes off. A double check is made by the crew chief and flight engineer. They manually test for cable locking. They also check the indicator on each of the 4 load levelers. The indicator on each leveler must be in the locked position. The load can now be lifted. This is done by the flight engineer raising the levelers to their full up limit using the walk-around control. The load should now be off the ground. Usually the load will sway a bit to center itself, and it may not hang level. The crew chief quickly adjusts this by using the walk-around control to raise or lower the individual load levelers until the cargo hangs level. At this point, the pilot should make a complete visual inspection before re-entering the aircraft. Before flying the load to its destination, hover the aircraft to check the center of gravity. In an emergency, the 4-point load leveler system cables on the CH-54B model can be sheared by guillotine-type cable cutters driven by explosive charges. Always remember, These guillotine-type cutters are to be used only in an emergency situation. The single-point hoist system has earned the CH-54 the name of flying crane. The system consists of a cargo hook that swivels 360 degrees, connected to 100 feet of usable cable. The cable is lowered and lifted by a hydraulically powered winch set in a well near the aircraft's center of gravity. In the CH-54, flight, hoist, and hook controls are not only available to the aircraft commander and to the pilot, but also to an aft-facing pilot who can fly the aircraft and operate the hoist controls from a position with a clear view of the load. These controls include a hoist up or down switch on all three collective pitch grips, a cargo release button that opens the cargo hook electrically is on all three cyclic sticks. The electric release button is the normal way used to open a hook and release a load. If the electric release does not operate, the hook can be manually unlocked by a ground crewman. In an emergency, the hoist cable can be sheared by a guillotine-type cable cutter driven by an explosive charge. This would be done after an attempt to electrically open the cargo hook had failed. An advisory light tells you when the hook is electrically unlocked. The flight engineer is an important member of the CH-54 crew and often coordinates picking up a load. Here's an example of proper communication between the aircraft commander and pilot in accomplishing load pickup. First, the crane is flown near the load and is brought to a hover. The height would, of course, depend upon the terrain. Now, communication begins with the aircraft commander's instructions to the flight engineer.
Close about 20 feet in front. Roger.
At this point, the flight engineer confirms position of the aircraft and advises the pilot of necessary maneuvers.
And I have the load in sight. Hold. Clear to come down 3.
The hook will stay closed until it is electrically released. At this point, the flight engineer confirms hookup.
He's got the hook, and the load is hooked up, coming up on the hook. Come to the rear 2 and center up a little. I've got the hook where I need it. We'll be clear to come on up and tighten up the straps. Okay, coming up. About 2 more feet and the straps will come in. And the straps are tight. Come forward 1 and right 1, center up final. And that looks good. Straps are tight and the load is off.
The pilot continues to hover until he is sure that the load weight is within estimated flyable limits for the mission. The winch tension indicator in the cockpit gives this weight. With confirmation of advanced calculations, the aircraft commander is sure that the mission is possible. Here's another important point. Virtually every load flown using the hoist will be a different experience. This quite often holds true when flying exactly the same load under very similar conditions. On one trip, a load may fly at one angle to the aircraft. On another trip, just 1 hour later, it may present an entirely different angle to the wind. And on the next trip, just a few minutes later, the crew may experience a totally different set of flying characteristics. This presentation on CH-54 flight operations would be incomplete without mention of a capability unique to the CH-54, the provision for limited flight control from the aft seat. Whether to use the aft-facing pilot is a decision to be made by the aircraft commander upon arriving over the pickup point. If the decision is made to utilize the aft flying capability, the procedure works like this. First, check the automatic flight control system. Be sure the AFCS number 1 and number 2 green lights are on. If the stick trim is not on, turn it on. Then move the hoist control on the center console to the aft position. Make sure the cargo hook release is in the shear hook position. Now everything is ready for the transfer of control. The pilot flies the crane near the load and brings the aircraft to a hover. Once again, height is dependent upon terrain. Bear in mind that correct cockpit communications are essential. Here's the right procedure. First, the pilot.
Are you ready in the rear? Jerry punching in normal mode now. I have a green light on normal mode. Okay, you have the aircraft. Okay, I have the aircraft. The hook is coming down.
Now the aft-facing pilot is flying the aircraft. But the pilot continues to monitor the controls, and he stays ready to take over. In an emergency, this can be done immediately as the pilot's controls override those of the aft-facing pilot. With a clear view of the load, a crashed T-33, the aft-facing pilot lowers the cable so the hook can be attached to the pickup rig. A ground crewman connects the hook to the lifting harness. The hook will stay closed until it is released. The aft-facing pilot lifts the load to a safe distance below the landing gear. When the load has been lifted to the desired altitude, he will return control to the pilot for takeoff. Here is the procedure.
Okay, you have the aircraft. I have the aircraft. Disengage remote stick. Okay, I've disengaged. Light is out. The hook is still coming up.
Now the pilot checks the load weight on the cable tension indicator. The load may now be carried to its destination. Here are key points covered in this presentation. Many variables will enter into the figures used to compute your maximum fuel load allowance. Weight and balance form Fs must always be completed when flying a pod-type load. A gap of approximately 1/4 inch must be left when the 4 pod safety pins are fastened to the fork assemblies on the airframe. This ensures that a pod will remain suspended from the load levelers, whose accumulators prevent vibration and shock being fed to the airframe. Before a pod or a 4-point load is lifted off the ground, always double-check the cables and the lock position indicator on the load levelers to make sure the cables are locked. Always use correct communications when aircraft control is being transferred between the pilot and the aft-facing pilot. Virtually every single-point load flown will have different flight characteristics. Before flying a single-point load, always check the load weight on your cable tension indicator. This presentation has covered some basic facts about flying the 3 types of loads carried by the CH-54. Flight operations have been shown with the B-model CH-54. Procedures and standards depicted are in general applicable to the A-model flying crane. The scope and type of missions flown by the CH-54 will increase as time goes by, serving to emphasize the importance of crane crews being familiar with and applying proper flight procedures.
Here in action is the CH-54 Tarhe. It is easy to see why the United States Army more commonly calls the Tarhe the flying crane. The Tarhe is a giant weightlifter with the strength to haul cargoes weighing as much as 10 tons. To accomplish their mission, CH-54s are powered by two gas turbine engines, takeoff rated at 4,500 shaft horsepower each. Lift is provided by a six-bladed main rotor system with a rotor disc diameter of 72 feet. In addition, the necessary auxiliary systems and their multiple components combine to make the Tarhe a complex aircraft. Inevitably, as in all complex systems, malfunctions will occur. Here we have a loss of power in one engine. In an emergency, the first priority is to maintain control of the aircraft, then determine the emergency and corrective actions. In this case, corrective action can be simple and effective. But crews of flying cranes should keep in mind that over 30 emergency situations may arise. You must know the correct procedures for handling every one of them. However, in this film, we will limit ourselves to 4 categories of malfunctions. That is, emergencies caused by fires, electrical failures, hydraulic failures, and engine failures. Let's begin with an internal engine fire on the ground. While starting number 1 engine, T5 rises fast and the fire warning light flashes on. The immediate corrective action, return N1 lever for affected engine to shut off. Ignition for engine on fire, off. Monitor the N1 RPM indicator. As soon as it decelerates to 25% or less, motor the affected engine by using the starter button located on the N1 lever. This should clear out the combustible materials. However, if the fire persists, move the fuel shut-off lever to off. Turn off the boost pump switch of the affected engine. Then once again, motor the engine by using the starter. This should extinguish the fire. Throughout the emergency, you must continue to monitor the T5. The engine must be shut down, even though the fire is out. Enter the highest temperature indicated by the T5 in the logbook and call maintenance personnel. Let us now consider an external fire occurring on the ground. The fire is around number 1 engine. In this case, the co-pilot calls the tower for assistance, and the pilot begins the shutdown. While awaiting the fire truck, place the N1 lever in shutoff, close the fuel valve, and turn off boost pumps, ignition switches, and battery. An external fire in flight would call for an immediate approach, simultaneously shutting down the affected engine, as in the ground situation. Now here's what to do for an internal fire in flight. This would likely be preceded by an engine failure. The master fire warning lights will flash on before both the pilot and co-pilot. Also, the red fire warning light for that engine lights up on the overhead engine control quadrant. Start an immediate approach to the ground. At the same time, instruct the co-pilot to shut down the engine on fire in this manner. First, pull the N1 lever for the number 1 engine to shut off. Then close number 1 engine fuel shut-off valve. On the center console, close the fuel cross-feed valve, turn off both the forward boost pump switches and the ignition switch for the affected engine. Now watch the N1 RPM indicator. As soon as it decelerates to 25% or less, press the starter switch to clear out the combustion. Keep the starter operating until all evidence of the fire has disappeared. Alert the crew to check for fire or smoke. When the fire is out, disengage the starter by pulling out the N1 lever. Since you are now operating on only one engine, you must attain a safe single-engine airspeed, then land immediately. Now let's examine the procedure used in the case of an electrical fire. In this case, smoke is occurring as a result of faulty wiring beneath the instrument console. Alert the flight engineer. If the cause of the fire can be isolated, pull the circuit breaker to the affected circuit. If not, turn both generator switches on the center console off. Then turn the battery switch off. This will cause a loss of all electrical power and should eliminate the hazard. If the fire continues, be ready to use the portable fire extinguisher. This procedure is correct for all types of electrical fires. Now let's take a look at some electrical malfunctions. A master caution light flashes on. A look at the caution advisory panel tells us that the number 1 generator is out. Reset the master caution light. Place the switch for this generator to the center, off reset position, and then move it back to on. This will return the generator to service if the failure was due to momentary overvoltage. If both generators fail, do exactly the same, using both generator switches. Usually this will correct the failure, but if both generators continue to remain off, you would turn off the generator switches, all non-essential equipment, and abort the mission, since the only electrical power source remaining is the battery. Here's a master caution light that proves to be a rectifier failure. In the case of one rectifier failing, simply turn it off. The primary DC bus is then powered by the remaining rectifier, and the monitored bus loads are dropped. But if both rectifiers should fail, the battery would power the DC primary bus, then turn both rectifiers off. And abort the mission. Now let's check out some emergency procedures used when the automatic flight control system has malfunctioned. This will cause the Tarhe to deviate in the pitch roll altitude or yaw channels. Besides this indication in the flight controls, the loss will be shown on the hover indicator. Here the pitch channel is malfunctioning. Corrective action: disengage the malfunctioning channel by use of the switch on the channel monitor panel. If this does not correct the malfunction, disengage the AFCS by pressing the auto stab release button. If you are still having trouble, you can eliminate the AFCS by turning off the AFCS servo. Another type malfunction is a hard over signal in any of the AFCS channels. Again, the hover indicator will show the one that is hard over. It is the roll channel. This can be overridden with the flight control. Disengage the faulty channel. If this does not correct the malfunction, Disengage all 4 channels by pressing the auto-stab release button. If the hard-over symptoms still remain, switch off the AFCS servo. Do not re-engage the AFCS system until the trouble is corrected. Whether you will continue to fly without use of the AFCS or with one or more of its channels not operating depends upon the importance of the mission. Here's another situation, a failure of the utility hydraulic system. You will be immediately aware of this condition due to the loss of the AFCS servo, causing the aircraft to become unstable. The master caution light will flash on. 2 quick checks will indicate that this is a utility hydraulic system failure. On the caution advisory panel, the AFCS servo pressure caution light and the first stage tail rotor servo caution light will illuminate. And on the instrument panel, the utility hydraulic pressure gauge will drop below the normal operating pressure. The emergency procedure in the case of this type of hydraulic failure is extremely simple. Press the auto-stab release button, disengaging the AFCS system. Then you land without use of the AFCS as soon as it is practical to do so. With the first stage tail rotor servo pressure lost, be careful not to inadvertently turn off the second stage servo switch on the collective stick. Another in-flight emergency is flight control servo hydraulic pressure failure. The master caution light will come on. Referring to the caution advisory panel, we see the first stage servo caution light is on. The failure is confirmed by a drop on the hydraulic pressure gauge for the same system. When this occurs, shut the defective system off using the switch on the collective pitch grip. Reduce your airspeed to between 60 and 70 knots and land as soon as practical. Loss of both flight control systems will make the aircraft uncontrollable. The flight control servo system also may fail due to a malfunction in the servo unit itself. In this case, it may be difficult to determine which servo system is failing, as both systems may be operating at normal pressure. So first reduce your airspeed to between 60 and 70 knots and begin an immediate descent. Then turn off one servo system to see if it is the one that is malfunctioning. But be prepared to return the switch to center instantly. Abrupt maneuvers may develop if the correctly operating system is turned off. If the second stage is okay, the first stage is obviously the faulty one and it remains off. You will, of course, land immediately. This completes a quick check of some emergency procedures used in the case of fires, electrical failures, and hydraulic failures. Now let's see what to do in the case of an engine failure. Correct procedure will depend entirely on the operating conditions. Some of the factors to be considered are the weight of the load and whether the load extends below the landing gear or not. And obviously, the altitude at which the engine loss occurs is of prime importance. However, in all cases of engine failure with loads extending below the landing gear, there is an easy rule to remember. The load should make ground contact with no forward and no lateral motion, as shown here. Or if the aircraft is in motion and gross weight prevents single engine hovering, the load must be jettisoned before it makes contact with the ground. Here is an emergency procedure to be used when an engine fails and you are hovering below 20 feet with a load too heavy for the remaining engine. One engine fails. Instantly, push both N2 engine trim switches up to full increase. If downward motion is not excessive and torque limitations are not exceeded, descend vertically and release the load as it touches the ground. After the release, move forward of the load and make a single engine landing. Here an engine fails when we do not have single engine hovering capability. There goes number one engine. Immediately increase both N2 engine trim switches to full increase. Ease the aircraft forward slightly using the cyclic control. Assume a landing attitude, then use the collective pitch control to cushion the landing. Apply the wheel brakes to stop the landing roll. After landing, lower the collective pitch to the full down position. If an engine fails before the Tarhe has attained an airspeed of 25 knots, remember that the emergency procedure is almost identical to the one for engine failure while hovering below 20 feet. Again, number one engine fails. Adjust collective to maintain rotor RPM with full increase on both N2 engine trim switches. Use the collective pitch to lower the aircraft and set down the load with no forward or lateral motion. After releasing the load, move forward and use the collective pitch to cushion the landing. Apply the wheel brakes to stop the landing roll and smoothly lower the collective pitch. This aircraft has just taken off, is over 50 feet up, and has attained an airspeed of over 25 knots. Then one engine fails. But in this case, you have enough altitude and a little more time to meet the situation as follows. To maintain NR, momentarily reduce collective pitch and push both N2 engine trim switches to full increase. Then increase collective to maintain altitude. If the terrain does not permit an immediate landing, increase power to the maximum and fly to a suitable landing area utilizing single engine procedures. Of course, if the load is too heavy for one engine and you cannot maintain altitude, you will jettison the cargo. Here's a situation in which the aft-facing pilot is hovering the aircraft. In many cases, this makes it easier to pick up and release the load. To be ready for any malfunction, the pilot and co-pilot monitor the instrument panel. The number one engine EPR decreases, indicating loss of power. Because of the limited control of the aft-facing pilot, the forward pilot takes over, as in all emergencies. The pilot then performs the necessary emergency procedures. Here's one more example of an engine failure. This Tarhe is cruising with a heavy load. Still, in an emergency, this load is light enough to be flown with a single engine. The number one engine fails. This can be quickly confirmed by a look at the torque meter and triple tack for the affected engine. To maintain rotor RPM, momentarily reduce the collective, increase the N2 engine trim switches to 100% NR, then increase collective to maintain altitude. Now, if possible, adjust your airspeed to about 70 knots. Then attempt an engine air restart if feasible. However, do not attempt to restart an engine that you know has failed mechanically. If it is not feasible to restart the engine, direct the co-pilot to shut it down in this sequence. Shut off the N1 lever for the affected engine. Fuel shut-off lever for failed engine closed. On the fuel management panel, close the fuel cross-feed. Turn off the fuel boost pump switches and the ignition switch for the failed engine. After shutdown, monitor the fire warning lights and the engine instruments. In this case, as in the procedure seen before, you will land as soon as it is practical to do so. We have just seen some emergency procedures used in CH-54 operations. The examples were for malfunctions caused by fires, electrical failures, hydraulic failures, and engine failures. You are not expected to remember everything covered in this film after seeing it only once. You will need to see it several times and to observe specific points as needed. You must also keep in mind that there are more than 30 emergency conditions that may arise during CH-54 operations. Eventually, all CH-54 pilots will learn to react instantly, automatically, and correctly in all situations. We hope that this film will be of some help towards making every flight in the CH-54 Tarhe a safer one.
The CH-54 Tarhe, more commonly called the Flying Crane, is the Army's most versatile heavy-lift helicopter. It may not win any beauty contests, but it more than makes up for its lack of loveliness with plain, hard-working utility. It can carry up to 25,000 pounds of external cargo, and it's unique in having two external load systems, a single-point hookup with a hoist and a 100-foot cable, and a 4-point load system for greater stability. It's also unique in having a removable pod for internal loads. The pod is about 28 feet long, 9 feet 6 inches wide, and 7 feet 8 inches high. It can deposit a pod full of cargo in one place and then go to a different location to pick up another load. This eliminates ground time during loading and unloading, and the CH-54 can spend more of its time in the air transporting cargo. When transporting the pod, the cargo hook is stowed on the left main landing gear. Preparation for single-point hookups consists of removing the hook from its rack. And then winching it up out of the way. The hook is on a 100-foot cable raised and lowered by a winch. In addition to the two pilots up front, the Flying Crane has a third pilot station which faces aft. This feature allows the CH-54 to be piloted from the rear seat if the situation arises. Normally, a flight engineer operates the winch from this station. Rigging an external load for a pickup by a CH-54 is basically the same as for an external pickup by any other cargo helicopter. For example, when recovering a disabled CH-47 helicopter, you possibly will use specially designed slings for recovery of this aircraft. These slings are attached to the hard points of the aircraft. To prevent the slings from flapping in flight, you will twist the slings one turn for every 3 feet of sling length. Then attach the slings to the hard point, making sure the pin is locked in place. At the top of the sling, make sure the keepers are cinched up tight. You will always use a large metal clevis to connect the sling to the cargo hook. The center of gravity of the sling load is always directly under the apex. This box has the same characteristics of a sling load. Using a fan to produce wind, we can simulate forces acting on a sling load in forward flight. Because of the relatively light weight and large surface areas of the box, it becomes violently unstable and uncontrollable in flight. One means of stabilizing the box is to add weight, which changes the weight-drag surface ratio. The box may become stable, but the box will still fly broadside, which will slow the aircraft down. Another means of achieving stability is by shortening the front two sling legs and adding weight to the forward area of the load. Notice the center of gravity is still under the apex, but has shifted to the front portion of the load, and the load will now fly with its smallest surface into the wind and with a high degree of stability. Whenever recovering an aircraft, you must remove or tie down all cowling. With some heavier loads, such as this Chinook, it is important that the load remain as stable as possible. A good method of achieving the stability desired is by adding a drogue chute with a swivel attachment to the rear, thereby streamlining the load and stabilizing it during flight. Someone must hold the chute when the flying crane arrives to keep it from blowing up into the rotors. The signalman brings the helicopter approximately over the load. The flight engineer or aft pilot now operates the winch and talks the pilot into position and lowers the hook to the hookup crew. You must use a static electricity discharge probe to ground the cargo hook for all single-point operations. The hookup crew climb off and move to the rear to assist in deploying the drogue chute. The pilots have an electrical release mechanism to open the hook to release the load. If this mechanism should fail, the CH-54 has an emergency release, an explosive cartridge below the hoist drum that will shear the cable. The hookup crew holds on to the drogue chute and deploys it when the CH-54 achieves forward flight. Practical factors such as time or the size and nature of the cargo may dictate a single-point hookup, but a situation may arise which dictates the use of a four-point hookup to achieve more stability in flight. In any helicopter operation, get the cargo ready before the aircraft arrives. Vehicle gas tanks are 3/4 full. Lower the windshields. The center of gravity is clearly indicated so the aircraft crew can complete the weight and balance data. Rigging for a four-point hookup is much simpler than for a single point. You need a lot less rigging equipment. In the front, you can use chains wrapped around the frame. Secure them with an L-hook. And for even more safety, use two chains. It is a good idea to secure the loose ends of the chains with nylon cord. Attach a large clevis at the top. Secure all canvas or any load in the truck with tie-down straps. The rear lifting point is at the tandem axles. Protect the aircraft's cable with a piece of canvas. It's the pilot's decision whether to set down right over the cargo or to have the cargo drive under the helicopter. The driver waits for the tail skid to be raised and for the crew member to guide him under the aircraft. Remember, do not set the handbrake on your vehicle before the hookup. The 4 lifting cables are 16 feet long, each on its own drum. One of the aircraft crew unlocks the drums with an electric switch inside the cockpit. We simply pull down the cables and place the hooks into the clevises. In the rear, you bring each cable straight down to the lifting point between the tandem axle. The drums are spring-loaded and take up the slack automatically. The flying crane has a load leveler system on the 4-point hookup. Operated by the air crewman's electrical control, each drum raises the load to clear it from the ground. When your unit requested the aircraft, you gave your cargo's weight and balance data to the air support unit. They'll now check to see that this data is exactly as you reported it. The air crewman makes a final check of the load before liftoff. For loading internally, the flying crane utilizes its removable pod. Remember that the pod weighs approximately 3,000 pounds, which you have to deduct from the cargo capacity of the aircraft. An internal load means you've got to make out a load plan. You'll find the necessary weight and balance information in the operator's manual for the CH-54 flying crane. Prepare a vehicle by reducing it to its lowest silhouette and tying down any projecting items. The pod has 2 doors for personnel, one on each side of the pod. The cargo door in the rear is secured by 2 locking levers. The door lowers to form the loading ramp. For heavy loads that exceed the bearing pressure of the pod's floor, you'll need load spreaders. Consult the operator's manual or other appropriate TM to see if your load requires them. Check to see that your load spreaders are clean and free of rocks or other debris that could damage the floor. A load spreader will also lose its effectiveness if it has a crack or split in it. Because of the reduced floor bearing area, whenever you use pallets, the floor can be easily damaged. An extensive repair to the aircraft floor will be necessary if you exceed the maximum pressure prescribed in the operator's manual. The rule of thumb when using load spreaders is that whatever the thickness of the load spreader, there must be an equal amount extending on each side of the load. On the basis of the information your unit gave, the flight engineer will prepare a loading plan. He will direct the placement of cargo so the helicopter will be properly balanced in flight. Loose cargo must be unitized with straps. If you didn't have pallets to pass the straps through, you'd have to lay the straps out on the floor first and load the cargo on top of them. Unitize your cargo completely. Each stack of boxes must behave as though it were a single piece. Use the CGU-1Bs for tying your cargo down. There's a formula for computing the number of tie-down devices you'll need in the appropriate technical manuals. You'll have to consider the cargo's weight, G-forces, the rated strength of the tie-down device, and the percent of effectiveness of that rated strength. The tie-down angle determines the percent of effectiveness. The rated strength is the weight the strap will hold if it's pulled straight out. Introduce an angle, and you reduce that strength. The flatter the angle, the greater the strength. A 45-degree angle is not as effective as a 30-degree angle, but the 30-degree angle requires more room. When you don't have that room, as here, you'll use the less strong 45-degree angle. You have to figure all this into your calculations. Study the manual before you get the assignment in the field. To lash heavy equipment, use the MB-1 with a 9-foot chain. It has a rated strength of 10,000 pounds. But the pod's floor rings are only rated at 5,000, so calculate your MB-1s as having only the 5,000-pound rated strength. For vehicles and other heavy equipment, use a 30-30 angle of tie. That is, a 30-degree angle up from the pod's floor, and a 30-degree angle off the center line of the aircraft. If the chain is angled outward, it's called an open tie. If it's angled inward, as here, it's a closed tie. Here's how you get the 30-30 combination angle. First, measure from the vehicle's attachment point down to the floor. Measure that length out from the vehicle, and then another 2/3 of a length. That gives you a 30-degree straight tie. For the other angle in the combination, measure one length to the side, to the outside for an open tie, to the inside for a closed tie. Again, use the nearest tie-down ring further away from the vehicle. The end of the chain with the L-shaped hook goes on the attachment point of the vehicle. Secure it with the loop facing upward, the open side down. There's a quick release hook for the other end of the MB-1. Install it by pushing the safety catch and turning the ratchet to extend the hook fully. Attach the hook to the floor ring. This butterfly mechanism is the quick release device. That must face upward. Pull the chain taut and hold the length in the hook's chain pocket. Ratchet the hook in as tight as you can get it with your fingers. Tension will now keep the link secure in the chain well until you pull the release lever at your destination. A Jeep will normally require 4 tie-down devices at the front to keep it from moving forward in the pod, and 2 at the back to keep it from moving rearward. Pad the chains where they cross. Use burlap bags, worn-out clothing, or, if it's the best you've got, even several layers of cardboard. An important part of any helicopter operation is policing the landing zone. Pick up all loose items. Notify air support of any hazards. Use smoke to designate the landing zone. If you've done some thinking ahead, you'll have the pod positioned with its front end facing into the wind. This reduces handling because the aircraft has to land into the wind, and you've got to approach with the pod from the aircraft's rear. Remove the pod's tow bar and push the pod by hand slowly under the aircraft to align with the 4-point hookup. The pod uses the same 4 hooks as does a 4-point external load. Simply hook each cable to the proper attachment point on the pod. You raise the pod's wheels by opening a hydraulic valve, and the wheels raise automatically. Before takeoff, the pilot will check the weight and balance data. He checks the load against the load plan to be sure the aircraft will be properly balanced in flight. He also verifies the destination and gets any special instruction that you, the supported unit, may have. The CH-54's cargo is by no means limited to hardware. It can also carry troops, but the pod must be adapted before it can carry troops. The aircraft crew does this by installing seats and seat belts. A crew member may ride inside the pod so he can drop the door as soon as the crane touches down at the pickup zone. The normal procedure is to approach a helicopter from the right side. Be sure that backpack antennas don't foul either the tail or the overhead rotor. If the operational situation calls for real speed, you may approach the flying crane from the right and left rear. Keep your squads together as you take seats. If you have less than a full load, space them to afford good balance. A member of the aircraft crew will double-check to see the men are properly strapped in. Just as it excels in all aspects of air transport, the flying crane's most striking quality is its versatility. It can carry equipment externally with the helicopter's conventional single-point hookup, or for greater stability with a 4-point hookup. One of its most important features is the pod, which can be removed and remain with the supported unit for loading or unloading, while the aircraft itself carries out another mission. This added on-the-job time in the air is invaluable. For as much as an Army needs food, supplies, and ammunition, it must have mobility. Supplying this vital mobility is the major talent of the CH-54 flying crane.
One
of the functions of the Army Agency for Aviation Safety is to analyze aircraft accidents to determine causes and then make recommendations to prevent similar accidents in the future. A study of Army mishap experience involving UH-1 and AH-1 helicopters shows that mass bumping in flight can cause mass failure and complete rotor separation, producing catastrophic accidents. Analysis reveals that mass bumping accidents can be prevented provided you, as a helicopter pilot, understand mass bumping and know what to do to avoid it. This film will first show what mass bumping is in the Huey and Cobra, then show the in-flight conditions which can precede mass bumping, and last, and by far the most important, how you can avoid mass bumping. It may be necessary to view the film more than once, for some of the required corrective actions are counterinstinctive. It is absolutely essential that you completely understand what causes mass bumping and what to do to avoid it.
In the Huey and Cobra, inappropriate pilot response to low-G maneuvers or mechanical failure can lead to mass bumping and possible in-flight separation. As an Army helicopter pilot, you must understand the operational characteristics of the UH-1 and AH-1 and know how to handle these aircraft to avoid mass bumping. To help you understand why mass bumping occurs and what you can do to avoid it, we'll first review some of the basics of the rotor and the control systems and the aerodynamics that lead to mass bumping. We'll then discuss these factors in terms of operational flight maneuvers and describe what you, as a pilot, must do to prevent the onset of mass bumping. First, mass bumping is the result of excessive rotor flapping. Flapping is the characteristic of a rotor blade to move up and down during rotation. Flapping is common to all helicopter rotor systems and is normal and expected. The rotors of the UH-1 and AH-1 use a seesaw action about a hinge pin to accommodate flapping. To prevent the blades from contacting the tail boom or other structure during normal starts and stops, the interior of the hub is fitted with static stops. These are contoured to limit the amount of blade flap, and sufficient clearance is provided between hub and static stops for all normal maneuvers. On the UH-1, the maximum flapping angle is just over 11.5 degrees. On the AH-1, it's 12.5 degrees. If flapping exceeds these values, the stops will bump the mast. It is the violent contact between the static stops and the mast during flight that causes mast separation, and this you must avoid at all costs. A turning rotor has a constant flapping pattern. Maximum flapping up will always be opposed by maximum flapping down, 180 degrees later. At normal operating speeds, the individual blades blur into a disc shape. When this rotor disc is not at a right angle to the mast, flapping is occurring. Now let's examine how flapping can occur as a result of pilot control inputs. The cyclic control stick transmits inputs through the swash plate, changing blade pitch. The rotor disc will flap in the direction the stick is moved. So, cyclic stick movement produces rotor flap. The pilot controls the position of the rotor disc. In flight, when the rotor disc tilts, the aircraft responds by moving in the same direction. In this way, the pilot controls the helicopter. Mast bumping is directly related to how much you, as a pilot, allow the blade system to flap. And to understand this better, we have to dig a little deeper. In straight and level flight, blade flapping is minimal and difficult to see in real time, or even, for that matter, in slow motion. Flapping angles of less than 2 degrees are expected under usual flight conditions. You can expect flapping angles to increase by 1 or 2 degrees with high forward speeds, at low rotor RPM, at high density altitudes, or at high gross weight. You can also expect increased flapping angles during turbulence. Aircraft maneuvering can also induce large flapping angles. For example, side slip and low speed flight at extreme CG positions. The risk of excessive flapping and possible mast bumping increases when you allow the aircraft to approach low G conditions. And that's what we really want to talk about. Let's see what happens when a pilot encounters a ridge line or a tree line, executes a cyclic climb, and then noses over using abrupt forward cyclic. In this maneuver, he has deliberately given up G loading on the rotor disc by changing rapidly from upward to downward flight and is approaching 0 G. Higher speeds aggravate the situation. The combination of down collective and low G means that lift, and therefore thrust, has essentially disappeared. Let's look at the situation from aft along the roll axis. Absence of thrust means there is no lateral cyclic control, so cyclic movement cannot change fuselage position. The aircraft does not respond because the pilot has given up G loading on the rotor disc. The thrust of the tail rotor, acting above the helicopter's center of gravity, starts the fuselage rolling to the right. Seeing this, the pilot wants to counter the roll, normally the right thing to do. Tail rotor thrust acting above the aircraft's CG will cause right roll rate to build up rapidly. Alarmed by the excessive roll rate, the pilot abruptly applies left cyclic. The rotor disc tilts in the direction commanded by the pilot. The pilot still has rotor control, but he is controlling an unloaded rotor. That is, a rotor that is not producing thrust. Although he still has fore and aft control, he has lost roll control of the helicopter. Flapping increases drastically. The rotor hub strikes the mast violently. On one side, then the other, and the mast may separate. Let's go back to the point where the roll started to see what the pilot should have done. As we saw before, as the aircraft rolled, lateral cyclic inputs could not develop thrust because there was no change in angle of attack of the rotor system with respect to the relative winds. Consequently, there was no positive lateral cyclic control. In contrast, let's look at the situation in the pitch axis. Similar to the roll case, aft cyclic inputs cause the rotor disc to move. But in this case, the disc movement changes the disc angle of attack. Aft cyclic realigns the rotor and thrust is restored. The nose pitches up. And with thrust once again available, the pilot is able to counteract the roll. Let's make sure we all understand what the pilot should have done during the nose-over maneuver. He could have avoided the low G condition by using more gradual forward cycling. The rate and extent of cyclic motion should be adjusted to keep the rotor loaded at all times. As a pilot, you clearly minimize the likelihood of mast bumping by staying above 1/2 G at all times, thereby preventing approach to low G and the right roll tendency. If the rotor becomes unloaded during low G, it is absolutely essential to recover thrust first by smoothly moving the cyclic stick aft. Once thrust is restored, left cyclic will then return the aircraft to the normal flight attitude. The basic lesson here is that the pilot contributes to the potential of mast bumping in the low G environment, because any pilot's instinctive reaction when a roll begins is to correct it with lateral cyclic. And the greater the roll rate, the more abrupt the control movement is likely to be. Severe flight attitudes seem to call for severe control inputs. Yet it's the severity of these inputs that can produce worse problems. If you encounter low G conditions, remember, avoid abrupt, large magnitude control inputs. Smooth, gradual control movements are essential. First, aft cyclic to restore the thrust. Then and only then, left cyclic to correct for right roll. You may also encounter low G conditions during mast unmasking maneuvers or steep descending nose-low turns. If these maneuvers are performed with abrupt, uncoordinated, or cross-control inputs, the rapid changes from upward to downward flight may unload the rotor and induce mast bumping. The risk of mast bumping also increases in turbulence when sudden upward and downward drafts can unload the rotor and get you into low G conditions. If that should happen, you must resist the instinctive urge to counteract unusual aircraft attitudes with hard lateral cyclic and pedal inputs. You must first reload the rotor by moving the cyclic stick aft. Then, once normal G conditions have been reestablished, normal control will return. But how about another possible cause of mast bumping? Engine failure. What should the pilot do to control this situation? Again, let's get back to some basics so that we can understand what happens. First, under normal conditions, and then when the engine fails. The actions we'll be talking about are complex, so it helps to imagine there's a camera along each axis, together with one behind the cockpit. At this moment, let's say the helicopter is flying in its normal cruise attitude. That means the longitudinal axis, and therefore the nose, is pitched down slightly, and the rotor disc is tilted slightly forward. From aft, the rotor disc is tilted slightly to the left to counter the rightward thrust of the tail rotor. The roll axis is located below the tail rotor thrust axis. From above, the main rotor rotation is counterclockwise. The resulting torque would force the nose to the right if it were not for the anti-torque thrust of the tail rotor and vertical fin. The airflow over the main rotor and fuselage would tend to raise the tail if it were not for the synchronized elevator. In normal flight, then, all forces are balanced and the helicopter is in equilibrium. From the cockpit point of view, the horizon is horizontal. Most engine failures do not result in mast bumping, but it can happen if the pilot fails to take appropriate action. Let's say the aircraft is in normal flight, all forces balanced. Then the engine fails suddenly. As the engine stops, the rotor RPM and airspeed both begin to decay, with some loss in altitude. Because the engine is no longer driving the main rotor and RPM is decaying, the torque about the mast that had been opposed by the tail rotor and fin is diminishing. So now, the tail rotor and fin, continuing to thrust to the right, causes the nose to yaw left. Interaction of the relative wind with the yawed helicopter and main rotor causes the aircraft to roll left. The pilot may see this as a nose-down tendency. The change in attitude has been abrupt and is continuing at an alarming rate. The pilot, responding to what he perceives as a nose-down, left yaw situation, reacts abruptly, but in the wrong manner for the case at hand. Right aft cyclic and right pedal, but he fails to lower collective. Right aft cyclic immediately tilts the rotor disc right and aft, and failure to lower collective results in decaying rotor RPM. This will result in larger flapping angles. Mast bumping may then occur. The remedy? Work on the primary problem, not the symptom. In this case, the symptom is the roll. The problem is power loss. So, when a loss of power is detected, you need to decrease the collective pitch to avoid a reduction in rotor RPM and apply sufficient right pedal to maintain a constant heading and enter auto rotation. But now, suppose you lose the tail rotor. In this case, the situation is practically a mirror image of engine failure. But it's further complicated because you've lost one of your primary control forces, tail rotor thrust. Let's see what happens. The instant the tail rotor fails, anti-torque thrust goes to zero, and only the fin remains to resist the torque about the main mast. The reduction in anti-torque thrust induces right yaw and left roll. Yaw attitude now exposes flat areas on the left side of the aircraft and the nose to the relative wind. This induces a roll to the left, aggravated by the absence of tail rotor thrust above the longitudinal axis that could have countered a roll in this direction. Almost instantly, the aircraft can yaw right, roll left, and pitch down. In this example, the pilot fails to lower collective to reduce the torque that is causing his aircraft to yaw. Instead, he moves the cyclic aft right again, working on the wrong thing, the symptoms, and not the problem. With the fuselage already rolling left, right cyclic tilts the rotor disc toward the fuselage and mast bumping threatens. The problem in this case is the torque tending to yaw the aircraft. The proper procedure in the event of tail rotor loss must be immediate reduction in power. You should then enter auto rotation. Power reduction will reduce the yawing tendency and therefore allow more time to correct the roll situation smoothly. With reduced throttle and collective, keep an airspeed slightly above the normal autorotative glide speed. You can experiment with gentle throttle and pitch application to see if some degree of powered flight can be resumed. But if any adverse yawing is experienced, re-enter auto rotation, continue descent, and land. For the past few minutes, we have reviewed some factors which are critical to your operation of the UH-1 and the AH-1 aircraft. We have reviewed mast bumping, what causes it, and how to prevent it. We saw that mast bumping is the result of excessive rotor flapping, and that the problem is directly related to how much you as a pilot allow the blade system to flap. We pointed out that the cyclic stick and swash plate make it possible for the pilot to control the tilt of the rotor disc. We saw that blade flapping is minimal in straight and level flight, less than 2 degrees under usual conditions. We then discussed how excessive flapping and possible mast bumping may be caused by aircraft maneuvering, particularly when you allow the aircraft to approach low G conditions. We explained that the rotor becomes unloaded during low G. We saw that the crucial issue was the loss of rotor thrust, because it's those times when the rotor is not producing thrust that lateral cyclic movement of the unloaded rotor disc will not only fail to control the helicopter, but can result in mast bumping. We then explained how to counteract the effects of low G by recovering rotor thrust first by smoothly moving the cyclic aft, then and only then left cyclic to correct for right roll. We also examined how engine failure or loss of tail rotor can cause mast bumping and the corrective actions the pilot should take, explaining that in the case of a loss of power, you should decrease collective and apply right pedal immediately to avoid a reduction in rotor RPM. Then enter auto rotation. Now, if the tail rotor fails, immediately reduce power, then enter auto rotation. The basic lesson here, and the single most important message that should have come through, is that you as a pilot can prevent mast bumping by the way you handle the aircraft. It is absolutely essential that your control inputs be smooth and gradual, even in difficult situations such as low G, because it is abrupt and full-range control inputs combined with mechanical factors that cause mast bumping.
It is crucial that you understand the operational characteristics of the UH-1 and AH-1 rotor systems and how normal blade flapping limits can be exceeded and result in mast bumping and possible mast separation. Again, I urge that this film be rerun until each and every one of you is completely confident that you know what to do to avoid mast bumping. Mast bumping is real, but it can and must be prevented. It is vital that you understand the part you play.